Welcome back, everyone, to this Ansys simulation software tutorial series. Today, we are going to be simulating a situation which scientists fear the most, a cantilever smartphone. In today's video, we'll be looking a little bit more at mesh fineness as well as using parameters as we go through this example so that you can get a little bit more experience with using Ansys. Okay, so let's go ahead and open up Workbench. Here we are. Today we are going to again be using a static structural analysis system, since that is what I'm covering in this series. We're going to be using two different materials for this simulation. So let's open up engineering. So the smartphone that we're going to be using in today's simulation is a Y phone, and it's by an imaginary company named Cherry. And we're going to be simulating for two different Y phones, the Y phone 115 and the Y phone 116. The Y phone 115 famously being made out of titanium, and the Y phone 116 being made out of simple aluminum. So to simulate that, we're just going to grab the corresponding materials from our engineering data sources. This is going to be under General Materials, and we are going to deselect, oh no, that added another structural steel. We'll delete that. We're going to add the titanium alloy and the aluminum alloy, those engineering data sources, and we're going to delete our structural steel. And these will be our two materials for this simulation. For geometry, I'm linking to the geometry in the description of this video down below, so you can go ahead and download that and then add that to your simulation so we can continue simulating. I'm just going to grab that from my files really quick. Cantilever smartphone. Do note that a .xt file, which is a parasolid file, is Ansys's preferred file format. So if you have something like a solid part file, which is what SolidWorks uses, just import that back into SolidWorks and then export it as a parasolid, or do something similar if you have a different CAD software. So let's open that. Then we're going to double-click Model to pull up Ansys Mechanical. Now that Ansys Mechanical is open, the first thing we're going to do is notice that this is not our preferred view. So we're going to spin this around here and set a new preferred view. It's useful to be able to rotate this just simply about an axis instead of having to do all of this weird stuff. So let me go back to isometric and then show you the best way to do this is to grab, and if you want your geometry to spin to the right, then you hold down middle mouse button and rotate to the left. If you want to spin to the left, rotate to the right. Then let's set this. So we're going to right click and click set. And that is our new isometric view. So if we ever want to come to that, we can click isometric view from the right click menu. So we need to set our geometry for this. It is all one body, so that should be pretty fast. Instead of creating material assignment, since it's only one body, I'm just going to click this, and we're going to set it to aluminum alloy. But since we're going to be simulating this twice, once with aluminum and once with titanium, I'm actually going to click the little P here and make this a parameter. So you can see under Workbench that this is now a parameter for our project. Now we can set a mesh. You can click generate and it will automatically generate a mesh. But as you can see, this is not a very fine mesh. So we're going to want something that is better. Although this can be useful for quickly getting a simulation going, just to estimate things before you actually run the simulation. So we're going to right click and insert sizing. Select geometry, that will be our only body, and element size. we need to decide on an element size. So let's select this. See if we can rotate this guy around. Because we want to use our little measurer thing down here. Goodness, I'm not sure what my graphs are doing. Select something random. So we can see that this is approximately 8 millimeters across. And as a rule of thumb, you want 2 elements across any given body. So we're going to use a 3 millimeter mesh here. That should be enough for at least 2. And we're actually going to parametrize this as well. We're going to do, actually I'm going to change this. We're going to do a 6 millimeter mesh, and then we're going to do a 3 millimeter mesh for whichever of the two materials, aluminum or titanium, actually allows the phone to survive. And then we're going to refine the mesh for that one that survives to see if the results change significantly when we use a finer mesh. So that is now available under here. We can see part 1 assignment, aluminum alloy, and body sizing, element size 6. So let's go back to our isometric view and generate this mesh. Shouldn't take too long. Now we are going to add some supports. So we can add a fixed support. We're going to use the faces, and we're going to fix all of these faces right here and apply. Back to isometric view. Now we are going to insert a force. So for our force, we're going to assume that some dirtbag in our college just walked up with a bag that has 153 kilograms of feathers because he decided that a kilogram of feathers was heavier than a kilogram of lead. And we are going to pretend that this jerk walked up to our delicate, beautiful, wonderfully crafted cantilever Y-phone and jumped on top of our iPhone's edge with his 153 kilograms of feathers. The 153 kilograms of feathers will apply a force of 1,500 newtons on the end of our Y-phone. How terribly sad. So for geometry, let's go ahead and apply this. We've got the magnitude. Now we're going to define the direction using this edge. And of course, we're going to insert deformation, total, and stress equivalent. And now let me make sure. Did I have, yes, aluminum alloy and 6 millimeters. So let's solve this and see what it returns for us when it's done. That didn't take too long. Let's look at deformation. This is how much it says it will deform, and this is the equivalent stress. The maximum stress is 326 megapascals. Now let's take a look over here under Workbench and look at our engineering data for aluminum alloy. The tensile ultimate strength, let's change this to megapascals, is 310 megapascals. So this means that our Y-phone, it reached its ultimate strength right here, and the 153 kilograms of feathers broke our poor Y-phone. So clearly the iPhone 116, which is made of aluminum, is not strong enough to withstand feathers. To avoid having to do this and just to get used to parameters, we're going to set the maximum equivalent stress as a parameter. Now that is not an input parameter, that is an output parameter. That means that instead of putting a number in, this will be displayed here. You can see there's a little out arrow, and under output parameters, we can see the equivalent stress maximum. So To try this again, let's try simulating the iPhone 115, which is made of titanium. Then we click Update All Design Points. This says some editors may close during the process. This is referring to Ansys Mechanical. And we can click Yes, and it will go ahead and solve that for us. And that shouldn't take too long considering how long the other one took. You can click Show Progress over here to see the progress so that you know about how long you're going to have to wait. All right, that's done. We can see that again, the equivalent stress maximum is 324. But if we look at our engineering data under titanium alloy, the tensile yield strength and the tensile compressive strength are both a wonderful 930 megapascals, meaning that the titanium iPhone 115 survived the feathers. Wonderful. Now let's change this parameter, the mesh sizing, to 3. Note the number here, 324, and see if that changes significantly when we update our model. Alrighty, that is done. We can see that when we change the mesh sizing, our result changed from 324 megapascals to a maximum of 343 megapascals, which is not significant enough to matter, but it could be significant enough to make a difference if you were dealing with really tight constraints and really low margins of safety, such as in rocketry. So you want to be careful of that. Just make sure your mesh is fine enough. It's good to get these initial results with coarse meshes, but when you want the actual results, you're going to want to put in a really small number and just let the computer take its time. So let's go ahead and open up Ansys Mechanical again, just to take a look at these results and see what exactly just happened to our iPhone when the feathers were applied to it. So we can see here the number at the top has again changed, and that is showing up here. Most of the stress is concentrated around here, and less of the stress is concentrated here, although obviously it has bent the most right here. View it from this direction and change back to true scale. And we can see that the iPhone has actually bent a noticeable amount from where it started. If we set this to undeformed wireframe, we can see that there has been a noticeable amount of bend right there. So now that we're done with this, we can save it. I did not save it earlier because I knew this would be a really short simulation, but we can just make this a holding folder and for smartphone holding folder. And this. Now you can tell all of your friends of your wonderful genius and your ability to simulate feathers smashing smartphones. Congratulations. That wraps up this wonderful and extremely useful tutorial on how to simulate phones being bent by feathers. Hopefully you picked up something useful from this and got a little bit more experience using Ansys so that you are well on your way to becoming a competent individual that can use Ansys to simulate whatever actual real-world situations come your way. As always, may the Lord bless your engineering. Come visit us at LU sometime, and feel free to move on to the next video, which will be on simulating forces on a popsicle stick bridge.